Good afternoon, ladies and gentlemen, and welcome to this webinar, Designing Concrete Elements Using Prokon SUMO Design Links. Quite a mouthful, but I'm hoping that it's going to be a nice practical webinar, or that is the idea. My name is Jacobus Oberholster. I'm an AEC and Prokon technical consultant with micrographics. You can see my email address at the bottom of the screen there. And of course, you are welcome to reach out after the webinar if you'd like any more information or assistance with anything. And then, of course, we've got a live chat going. So I would encourage you to pop any questions you have in the live chat, and I will be sure to make some time to address those. If I can't address them in this particular or on this platform, then what I'll do is we'll just find a way to get hold of each other after the webinar, and then I can answer your questions. So, right, without further ado, let's jump into our agenda. So just a nice brief one where we're going to look at our model introduction. We're going to look at the beam detailing design link. We're going to look at the subframe design link, the rectangular column design link, also showed as rec col, the circular column design link, base, and pile cap as well. And then one that we're missing there is the general column design link, which is for the design of custom shaped columns or columns that don't fit to within the scope of rectangular or circular column. So, all right, let's jump into SUMO, and we have got our concrete model over here. And what this model contains is essentially all of the elements that we can design using the design links available over here. So what you'll see in this model, you'll see, of course, slabs. Now, there isn't a slab design link yet, fingers crossed. But what we've got at the bottom, we've got our bases, we've got circular columns, we've got normal rectangular columns, we've got monolithic beams, we've got custom beams. So we see it's got two rounded sides on each edge. We've got custom beams at the bottom here. So if I just switch off beams quickly, you can see these are square columns with a hole in the middle, whether that's for conduits, rain pipes, whatever might have you. But we've got subframe strips as well. You can see a subframe strip or part of a subframe strip running over there. And we'll discuss some of the workflows that you need to remain aware of when it comes to subframe strips. So if I go to analytical modeling, not analytical modeling, but rather my analytical model view, you can see we've got two subframe strips over there, and we'll discuss those shortly. All right, so the first thing is we've already run an analysis. That's why the results workspace is visible over there. We've got our standard dead load and live load cases and one load combination. And when it comes to the base or using the base design link, I will add one more load case to simulate wind force pushing the structure upwards, because it's something I'd really like to make you aware of when we use the base design link. So right, but our first design link is beam detailing. And oftentimes there is a bit of difficulty with the beam detailing design link because we try to use it to design monolithic beams. Now, in general, the beam detailing design link is not best suited for the design of monolithic beams. All right, it's not impossible. It's not a taboo per se, but it isn't specifically what the beam detailing design link is suited for. All right, we'll get to subframe strips after this. Now, if you look at these beams on the side here, so just beams that brace these columns midway, and we've got some beams up here and a beam running right in the middle. We can see quite a large set of point loads there and distributed loads. And this is where the beam detailing design link comes into play. So if we select this beam, right? We've got its properties over here. We've got its start and end fixity. All right, so what we'll do is we'll click beam detailing, select this beam, press enter. Wants to know what percentage of these loads are permanent. I'm just going to set 100% as permanent and 0% redistribution. I'm happy with the rest. I'm going to click OK. So what it's doing now is it's taking this geometry as well as the load effects from the analysis into continuous beam. And one thing that you'll notice at this stage with the beam detailing design link is that the input and design tabs are grayed out. The reason for that is the beam detailing design link, I'm going to twist my tongue with that one, imports load effects from, or rather analysis results from SUMO. If anything changes in the geometry, it renders these results null and void. All right, of course, because the self weight would have changed, etc. Now, we can see these results from here. So moments in shear, we can see M max over there as well, 128.9. If we go back, we go to results, beams, X moment, we see that we are essentially there. All right. So going back over here, we've got our M max, our V max, and then we look at our deflections, and there's something quite odd with this elastic deflection, right? It seems like, because this is the deflection envelope over here, it seems quite consistent, and that doesn't really make sense, right? If we look at the long-term deflections, this makes more sense. Now, why is that the case? Okay, so I'm going to close this. So just take note of what this elastic deflection graph looks like. If we look in our results workspace, we look at deflection or displacement, we can see that this beam is not deflecting. But if we look at the loads imposed on that beam, surely this beam must deflect. And the reason for that is quite simple. If we go into the beam, we go to its properties panel and we look at its segments, we see that it's only one solid segment. Deflection is calculated at nodal points, and what we want to do is increase the number of segments, which splits this beam into smaller segments. Of course, adding more nodes to the beam, which results in a more accurate deflected shape. So I'm going to say segments 10. After now, reanalyze my model, and then we'll go back to the beam detailing design link. So just waiting for this to finish. Right, the reason this is taking so long is because of all of the slabs with their meshes. That's why this is taking a bit longer than expected. This is just a normal linear elastic analysis. So I'm just waiting for this to complete now. Now, just as while we're waiting, this idea of segments is incredibly important for accurate deflection, and it's something we must hold dear to, well, hold in mind when it comes to looking at our analysis results. All right, so firstly, just look at the displacement. We can see there's improvement in that displacement. I'll go to design links, beam detailing, select that beam, and I'm going to set these values to 100%. All right, and click OK. Now, when we look at the deflections, it should have a more realistic elastic deflection, and you can see that over there. From just changing the number of segments, we have added or contributed to the accuracy of our model. All right, so we're in continuous beam. We've got our moments, shear, and deflection values. And of course, if we look at this M max now, 130.6, if we go back to results and beams, we see there 130.6, which is so interesting because there was a slight difference, almost a negligible difference between M max previously and now. and it can actually be, we could very likely attribute or can't attribute that to the number of segments. But all right, we'll go to our detailing parameters. We've got beam type, etc., etc. And generate reinforcement. We can see all of that over here. We've got our nominal versus required steel, and then the red is provided. We go to 3D view, and there we go. Now, just to show, if you look at these ends, and I think it's just something that requires a bit of improvement, but you could see there's a grade plane here, and then the bars extend beyond that grade plane. And this side, you've got that gray plane, which of course is the end of the beam, and the bars extend beyond that. The reason for that is, if we go to main reinforcement, you can see that this is the span, these red lines. We're in the column, and of course we want these bars to extend beyond the center line of the column. And that's where you see that minus 0.125 offset and the length of 4.75, even though the span is only 4.5 meters. Right, so what I would have preferred is if we had this little gray block, this additional block on either side, or if both of them didn't have the gray block as it is with the red, the right hand side. Right, just so you know, that's why it looks this way, and that's why those bars extend beyond the center line of the column. All right, so with that, that's beam detailing pretty much done and dusted. With adjusting the main reinforcement, stirrups, shear reinforcement, etc., that is all as per normal. All right, now we're going to start looking at subframe strips. Right, now subframe strips are incredibly cool in that they isolate this portion of a slab with all of the relevant geometry within that net, we can say. It isolates all of that, takes it to continuous beam from where you essentially do your analysis and design from scratch. Okay, very useful for designing things like T-beams, etc. But there are some important things to take into consideration. Right, there's a clicking order, etc. that's very important. The cool thing is, it will pick up if there's circular columns, etc. The subframe strip design link has been improved significantly, and it is way more it's way better than what it was before. So what I'm going to do at the bottom here is I'm going to insert a line, and then I'm going to extend that line to the edge of the slab. Do that both sides. All right, we've got a line extended there. I can select that line, change its color to red, and make it a nice solid line. All right, and then maybe switch off the load cases so that it just looks a bit better. All right, so they're not gone, they're still there, they're just not visible. All right, so now I'm going to go to subframe strip, and the left and right values are the values, basically the tributary width on either side of the subframe strip. So if we check in this scenario, if I just measure between these two columns, we see it's 5 meters, so the tributary width on that side is 2.5. On this side it's 6, so the tributary width on this side is 3 meters. So I'm going to subframe strip, left 2.5, right 3, and I'm going to start by clicking once on the edge. Then wherever there's a column intersection, I am going to continue on clicking until I get to the very end. When I get to the very end, I'm going to press the enter button, and you have to see these horizontal lines to know that you've placed your subframe strip correctly. Once I see those lines, I'm going to click on accept. You have to hit enter first. And there's our subframe strip. Importantly, a subframe strip is only in one direction, and you'll have to have subframe strips in the other directions as well. Now, a cool thing about a subframe strip is that you don't need to run your analysis in order to use it. So I'm going to say subframe, select that subframe strip. Actually, I want to change its fixity, end fixity, so that's the start at the end. I'm going to change the subframe strip's start and end fixity to free because it is a cantilever section or an overhang. So it sees point loads, line loads, and plane area loads are apportioned to subframe based on geometry without consideration of transverse stiffness. Right, the magnitude of these loads should be checked. Right, so no transverse stiffness is taken into consideration, and that's pretty much how we design by hand. We isolate portions of a slab, and whether if it's a one-way slab, it's a meter wide beam, and we don't consider transverse stiffness at all. You can see a little picture there of the model as it is. It looks great thus far. We can go through our sections, and you can see that it plots all of these different sections. You can honestly delete all of these as long as they're all the same, and just apply the same section number throughout all of your spans. We go to spans, we can see all of these different spans. There's the overhangs and where we expect the columns to be. And the cool thing is with the supports, you can see that these ends are now cantilevered. There's our circular columns, and then the columns on the floor above. The loads are pulled in as per the as per what is within that net. And all that we must do is we must just make sure that we assign a dead and a live load case to these different loads. So if I go back now and I just want to switch these load cases on again, just want to see what is the magnitude of what. So the live load is smaller than the dead load, right? So we're going to start off with dead, live, dead, live, dead, live, dead, live, dead, live. All right. And also something to keep in mind in continuous beam is that continuous beam does apply pattern loading. All right. So that is something to consider. It generates envelopes with pattern loading. It does that automatically. All right. Here we pretty much made all of the changes we need to make. We can go to design. We can see our elastic deflection. We can see long-term deflections, and the long-term deflection does update when you generate your reinforcement. At the moment, it's just using the required reinforcement, and this blue line here is the required reinforcement. We can see there's no need for, there's no shear requirements here, which actually makes sense. We can go to reinforcement. We can say generate reinforcement. We can say we actually applied way more than what we need to. So I'm going to go back, and I remember that this was just a piece of slab. So I'm going to change the beam type to slab, generate reinforcement, and this looks a lot better. I'll have to make some changes over here to make sure that those red lines are above the blue lines. And with that, I can either add additional bars or increase the size of those bars and the number of. So let's make that something like 10, for instance, maybe 12. All right, 12 is good. I'm going to go to this one, make that one 12 Y20s. And I am happy. I could even reduce those in the bottom a little bit. Right. Stirrups, there will be nothing because this is detailed as a slab. Shear reinforcement, of course, nothing. And then in sections, there is really nothing to look at in this case. We go to our 3D view. We can see there's our slab. There, it's pushing out over the edge slightly, which is something we can fix quite easily. But you can see this is our bar, the required bars distribution, and that looks great. Of course, we know that we'll add nominal bars here to bind all of the bars. We'll have stools, etc. And then, of course, because this is one way, we'll need to do it in the other direction as well. Okay, so this is just the basics of subframe strip. What I want to take us to next is if we have a monolithic beam. Right, so in this case, we've got two subframe strips. Now, on this side, the green one, you can see that each one of the monolithic beams is a segment between the columns. On the left-hand side, it's one continuous monolithic beam. Now, that is not a negligible point, because if I export the subframe strip where I have the monolithic beams in little segments, I'm going to pick up an issue. So I'm going to go to design links. I'm going to say subframe. Select that subframe strip where the monolithic beams are little segments. I want to set the start and end fixity to free again. Oh no, wait, in this case, no, it's free. That's all good. 3 is good. And enter. Just the same notification as before. And you could see if I go, just going to generate reinforcement and go to 3D view, you could see in this case something weird happens, and we only have one segment of that monolithic beam on this side. Right, that is why it is best practice of using subframe strips that you use one monolithic beam from the start to the end of where the subframe strip will be. So now if we take this subframe strip, we'll see a different story. And then you can see that beam is running straight through. If we go to reinforcement, generate reinforcement, and 3D view, we can see here, this is exactly what we want. There's that beam running straight through. All right, so it's not negligible. It is something important to keep in mind. All right, but just looking at our model in SUMO, we can see that there's been a cutout over here. So there's some shaft coming down here. And if we go to continuous beam and we just look at our 3D model, we can see that that cutout isn't anywhere. So does the continuous beam design link pick up that cutout? Well, in some way it does. If we go to loads, we can see that there's a dip in the load magnitude in this area, in span 2. And that is where that cutout is. So if anything, it does pick up that there's a reduction in load. And the reduction in load is for both the dead load and live load because they're applied over an area. So it's definitely picked up, but we can go and make adjustments to correct it if we feel like we have to. So I'm just going to change these. So dead and live. Dead, there we go. Then this one is going to be a few values of dead, and then the rest of these are live, and then dead, live, dead, live, dead, live. Okay. All right, we can see there's a little dip here. We do expect it to be vertical, which is interesting that it doesn't do that, but it's not the worst thing in the world. All right, so if we go to sections, we could see we've got a ton of sections over here. I'm going to delete these, and I'm going to create one more section. I'm going to apply 250, 750, 3500, 250, and then this one, let's see, 250. Yeah, there we go. Okay. So 50. There we go. Okay. 875. This would just be based on measurements I took of this cutout, etc. All right. So those values you would measure on within SUMO itself, and you'll know where to apply them. All right. So I'm going to go to spans, and I'm going to apply the same section number throughout for now. All right, and then here with span number 2, I am going to add 2 more lines. This length is going to be 0.7, 0.7, and then let's measure this distance. Let's see quickly. Six meters. All right. So then it's going to be 4.5. All right, so this is pretty much what that input looks like. It's all still on the same span, but there's multiple sections within the same span. So now we go generate reinforcement, go 3D view, we can see that cutout over there. All right, so that is how you'd go about modeling that cutout in continuous beam if you use the subframe strip. And I'm a big fan of the subframe strip. I think it is super convenient. You must just know which one between beam detailing and subframe strip is the applicable one. And if you try to use this for something that it's not really meant for, you are going to find, well, you're going to encounter some frustration. There are workarounds, absolutely, but the subframe strip is more flexible. It takes a bit more groundwork, whereas beam detailing is a lot more streamlined, but of course you cannot modify the geometry or the loads at all. All right, so that's subframe strip, pretty much done and dusted in beam detailing. So we need to run our analysis again to proceed with the other design links. Right, so what we're going to do next is we are going to look at our 3-column design links, and just something to remain aware of when using the column design links. All right, there's a specific limitation here, and unfortunately it doesn't explain 100% what that limitation is. And we'll have a look at that shortly. So see here from Jean-Jacques Kriel, is it possible to insert width lines in the SUMO models to import the correct section geometry for continuous beam? Jacques, I do think so. It's not something I've tried out, and if we have time, we can actually check with putting width lines over here and seeing exactly what happens, so that actually models that cut out for us. I suspect so, and we can have a look at that in a little bit. All right, so let's go to our design links. We have rectangular column, circular column, and general column. We've got some custom columns over here, and we've got rectangular columns pretty much throughout the building. At the bottom floor, we've got our circular columns. All right, so over here, we've got this beam coming in on the side of this column. I'm going to set red column, select that one, and there is an error. One column / cons with discarded due to connections along the height. Okay, so the program only wants to work with end moments. So what you do in this case is you split this beam in half, this column in half. So 3.2 be 1.6. I'm going to select that column and copy it on top of the other, and we'll have exactly the same effect. Right, so it will make no difference in your analytical model, but you'll pretty much have to export them, or you can only export them when they split like that, if they have any connections along the height. The same can happen if you have a line load that doesn't run over the full length of the column. You can have a problem as well. If anything splits the column with nodes, which loads can, you're going to have a problem. So wherever you have anything coming in laterally, or anything that splits the column into more nodes or more segments, you have to split that column physically like this. All right, so if I go design links, I go circular column, let's select both. Oh, I select the circular column. Apologies, I was just saying no ways. There we go. Okay, so here's just our conditions, brace, etc., etc., etc. I'm going to say okay. All right. What it's done here is it records the length or the height of one of the two sections, and then you have your ULS design loads here for each of those sections. Okay, what you can do then is you can just increase the LO to 3.2. All right, so nothing too much, or nothing that is it's not nothing complex to solve. You just have to get into the design link, and then you can make modifications over here. All right, and then we've got all of our loads here, which is fantastic. We can then just go design and work through it as per normal. All right, so that's rectangular column, and it'll be exactly the same for circular. So if I select circular and I select one of these columns, of course, the more columns you select, the more of the analysis data will be captured within the loads table. All right, so if I select all of these, actually, as long as they are the same profile, you shouldn't have any major issues. right? What I would recommend in the case where it's different profiles is, of course, you group them according to their profiles. And you can see all of that data is captured, and you know that what you will be designing for is the worst case of those columns. All right, and this then just go through the process as it did with rectangular column. All right, now if we look at custom columns or the general column design link, it needs to be a custom shape. Okay, so general column works on first principles, and it allows you to design any shape concrete column, right? And what some people have done is they take the conventional shapes and run it through general column as well, which is fine. But the reality is, if it's not a custom shape, meaning it's not located in the custom sections part of your sections database, you cannot send it to general column, right? So if I say gen column, you see one columns were discarded. The design link only supports the type custom section, right? So if we go to standard sections, we add sections. Here's our custom concrete sections. It has to come from this table, and of course through ProSec you can add additional custom profiles. All right, so we're just going to look at these ones. I'm going to go design links, general column, select that column over there with the hole in the middle, whether that's conduit or rainwater, whatever it might be. Let's say okay. And then what's brilliant about this is that it builds the profile as it is within general column. And there we've got our profile over there. We can add our bars. So if you've worked in general column before, you know that you need to add bars via this input over here, and then you can design it. Right, so really, really cool. It records a lot of the data, and of course there's some things that you can just change here, whether it's the end conditions, etc. The end conditions do relate to the fixity, the start and end fixity of the column itself. So just something so that you know it's not always going to be fixed. If you've changed the fixities of these elements, it will record that in the design link as well. Right, second to last, we have our base design link. So we've got a whole set of bases, and of course if you select all of the bases, it will do exactly the same thing it did before, where it records all of that analytical data. So I'm going to select this base with all of its geometry. It's got a nice circular stub column there, basically just modeled in as an extension of the circular column. I'm going to click base. There's a lot of stuff I can change over here, which is quite odd for me. I'm not 100% sure why I have all of these options over here, but they're there nonetheless. I can say okay, and we'll export the geometry with its data to the base module. And you can see base length, base width, and everything is recorded here, as well as the load factors, which is brilliant, along with its load effects. So you can see over here, it records the load factors for the combination. So it breaks those load effects up into its respective components, live and dead, assigns the relevant load factor, and we can change this to see. So we can go back, go to standard load combinations. I'll make this 1.5. Let's run through our analysis. You know what? I am going to change the mesh size of these slabs so that the analysis runs a bit quicker. All right, there we go. Okay, let's export our base quickly. Let's hope. Let's hope it records it. And there we go. You know, I always get so nervous. I'm like, man, sometimes it's just a glitch and it makes you feel like you've got egg on your face, right? But here we go. There it records that load factor for the relevant load effects, and it records the different load cases as well, which is epic. And this way you can run through your design process, run through all of your checks, of course, The only difference here is, so let's say I'm going to go optimize A. I'm going to make that one 2.1, and then let's optimize B. Okay, 2.1 and 2.45. So now the dimensions of this base have changed. Because it's just a normal design link, it won't update the basis geometry within SUMO. And that's where your design link groups come into play, or your design groups. Right, so once you've created a design group, it works through the same process as your design links. So let me create one here. I'm going to add all of these pad footings to that design group. So rather than a group, it's a design group. Let's say design. It will now take all of that data into base. Of course, you can again assign groups. I can go optimize A, B, and Y. So we're just waiting for it to run through the optimization. I'm hoping it's going to optimize it, because usually what happens, I've at least noted, when I've done optimize A, B, and Y, the program has crashed. Right, so let's hope. Okay. Brilliant. Okay, so change it now to something quite small. Doesn't make a significant difference actually in the shape. All right. But these are 2.5 by 2.5. I'm going to save this one. Close it. Select one below. And I don't know if you noticed, but all of these footings adjusted their size. So they used to be 2.5 by 2.5. You can see they're now 2.5 by 2.4, and the depth hasn't changed. And that really is the power of a design group. And I hope that when there's a new big release, that they will add more design groups to SUMO, because they are really fantastic. The same with Combine, even though that's now outside of the scope of this training. Combine actually allows you to check all of your steel sections and optimize them and replace them all within SUMO itself. All right, that's base done and dusted. What we can look at next is pile cap. And what you can imagine is that this base is a pile cap just missing the piles beneath it. Right, so if I go pile cap, select the base, and I'm exporting that to the pile cap module. And unfortunately, it does not yet record the geometric data of the actual cap itself. So I'm just going to add some data over here. And there we've got our pile cap. Okay, because this is not a design group, it won't update anything if we change anything in its geometry. So basically what we can see in SUMO is this upper section, but it records all of these loads for us, which is fantastic. Now, in this case, it seems to be quite misleading, because it says these are unfactored loads. So let's have a look. So we can say that's 1270 for C1. So that's that one over there. Go to results. I'm hoping I'm going to look at the right one now. Okay, there's 12756. So it will record this data as it is in its seemingly dead and live load components without assigning any factors. And that's just something to check whether or not these are actually factored, and it's just assigning a load factor of 1. Okay, so if these are already 1.2 and 1.6, just to make sure of that. Okay, so I know that that was a big change they made to base, which we just saw. And that is an important thing that's changed in base, so that it actually records the load factors. where it's possible that it doesn't yet record the load factors in PileCap, and always something important to check anyway. Okay, I see a question there. Would design strips work across slabs with different thicknesses? Well, let's have a look. All right, so that is PileCap done and dusted. So that's pretty much our design links. And so what we're going to do is let's now answer these different questions. Okay, so I'm going to have to create a cutout somewhere. So let's go to level 4. I'm going to cut out a portion of this slab over here and replace it with a thicker slab. So I'm going to select it. Okay, let me actually just bear with me as I do this quickly. Oh. I just need to give myself some reference here for the cutout. All right. Now we're going to offset these. Okay, cool. We've got that. I'm going to select the slab, click modify. That's good. It's continuous. And I'm going to select these sections over here. All right, and we've got our cutout. Okay, so now we're going to add a slightly thicker piece. So this is 250. Go to, I'm going to delete these lines quickly. I don't need them. Excuse me. All right, let's go here. We'll make this significantly thicker. Let's do 400. And I'm going to add that slab in there. Okay. All right, so one of the things you need to know is that in its 3D model, if you try to align its top, so well, whether you're trying to make the soffits or the top flush with each other, you're going to mess up the subframe strip workflow, right? Because the moment this elevation changes ever so slightly, so if I make this 13.3, okay, which is not quite flush yet, but the moment that elevation changes, your subframe strip will no longer pick up that there's a slab running over there. All right, it works on the analytical plane. So I'm going to insert a line just for reference again, and we'll see what it does. It's interesting that it's not wanting to extend all the way there, but that's all right. We can just fix that quickly. Interesting how finicky this has become just with that over there. But all right, we actually don't need these edges. I'm not going to mess around with that unnecessarily. So I'll go subframe. I'm just going to make these 1.5 aside. And it might come down to where we need to click. So I'm just going to make sure that I select all the relevant points. And we've got, where's our column over there? Okay, so we've got our width lines over there. They're touching that slab. So let's see. Let's hope for the best. I'm going to go subframe. Let's see what it does. Okay, so it does actually pick up that slab thickness. You can see that that is over there, and it's applied a Y offset for us. So if I go to reinforcement, click generate, and 3D view, let's see what it's done. Okay, so it has applied the Y offset for the wrong slabs. Okay, so we can go and adjust that. So I'm going to delete these chaps. And I'm going to say these oaks let's hope this is, or maybe it should be downwards. There we go. Okay, I'm hoping this is the one. Let's see, reinforcement. Okay, not quite yet. What is this? Why offset is now just being troublesome for no particular reason. Should be a bit less than that actually. We think 250, so 75 only actually. Let's see. I think I was a bit eager with that one. So are we still not there? Oh yes, okay. Guys, I completely forgot that the offset, it will automatically align the tops of the slabs without any offset. That's why it is messing me around as much as it is. So you can see that without any offset, it aligns. Ooh, let me change those parameters quickly. Right, there we go. All right, that's much better. You can see that it aligns the tops of the slabs. And the only thing where you would need to pay a bit of attention and maybe make some modifications is where it thickens, where you'll have to position bars and just change this up a bit. You can always do it in the main reinforcement window. You can see that's over there. It's nice and exaggerated actually. And when you add bars, you will see that they will still update as per the graph to make sure that you're applying the correct amount of reinforcing. My concern over here, let's see if it adds a bottom bar. This, okay, don't want that one there. There we go. Okay, so it fits in quite nicely over there. You must just reduce its length a bit. If we go to 3D view, we can see that bar over there. All right, so it can be done. And then lastly, what we just want to make sure of is that if we increase the number of this bar, that this red line moves. Right, so if I go to, and you can see that the red line does move. Okay, so it does pick up that this contributes to the required area of steel. So Yashiv, I hope that that answers your question, and I am elated for a good outcome. Okay, now lastly, John Jock, what we'll do, this thing is now, there we go, okay, back to normal. We'll see whether or not, if we can actually modify these width lines, which I'm hoping is not going to be too complicated. Right, so I'm going to add this one. And to get the order right of this one, I don't often use the width line. Right, there we go. Enter. Okay, now the width line we can set as, I think this, let's do 2 meters and 2 meters over here. To plot the width line quickly. Okay, I actually need to add some lines, so just give me a quick second. I'll need some reference lines, otherwise I am going to have some difficulty over here. And let's make these guys just 2 meters aside. All right, and the same on this side, 2 meters. Okay, I'm going to change them up a little bit as well, just so that they have a nicer color, nice and solid. I'm going to delete this one because I don't need it. Let's go for lime, solid, that's good. And I'm going to add this guy over here, over there, over there. Very interesting question, Jock. I've actually not even thought of trying to test out these width lines. Okay, let's go for subframe strip. Make these 0 and 0. This line, there we go. Okay, let's hope. Okay, that's all right. Let's see what this is going to do for us. It could well be that we're going to have some issues with that one sloping in on the side. But let's have a look. Yeah, there we go. So good news all around, which I'm quite elated for, even with something that I honestly haven't thought to even check. But let's see what our 3D view looks like. Okay, those ones we can solve just with how we place our width lines, so that's not something to be concerned about. But you can see with rather placing width lines, we actually mitigate the need for that process that we followed right in the beginning, which is quite cool. My thing is, what I suspect is that the width lines taper in. So if we look in this case, you can see that it actually tapers in to that point over there. And I am not 100% sure if that is something that we can mitigate. All right. It might be under these circumstances. So it's interesting how it does that taper. I have a pretty good idea of how it does that. Yeah, it just does. Let's do section 1, 3, 1, 1, 8. Okay, where is the tapered one? Sections, it is section 4. Okay, I'm going to use section 4 over here instead of 3. Okay. Yeah, I get what it's going to do now. Okay, we can swap that around. So just, why is that? Let's go for it, go for it. Oh, yes. Goodness. There we go. I'm not reading these section links properly. Okay, if we go there now, it should be all good. All right, so a minor thing that you'd need to change with it so that they don't taper, because they do taper. Instead of going straight up to that point and then going back, maybe there is an adjustment of how we place the width lines that might be necessary. Maybe. I am not 100% sure, and that is something that we would need to play around a little bit. But I do think that this is a quicker way of actually resolving this issue. Okay, so with that, and just the good outcomes of the questions that were asked, we are concluding our webinar. So sorry for the abruptness. Actually, we was going to stop at just our pile cap, but with these that we tested out, we've had a nice successful outcome there. So yeah, thank you so much for watching. Yashif, I will answer your questions shortly. I'm just going to have those that wish to go, that they are more than welcome to go. But I do appreciate you guys turning in, and I appreciate the questions. It really makes for a way more engaging webinar. And yeah, you're welcome to, of course, send me a mail afterwards. and we can chat. And please remember to like and subscribe if you haven't already. And then I look forward to seeing you in a future clip. Then Yashiv, just with your question on available information on solid elements for general FEA in SUMO, we do have, if you look at our channel, you'll see here and there we have a clip, or actually I can think of only one, where we recently looked at the comparison between code-based values and FEA results. There's another webinar on that you'll find on our channel, where we do look at using solids. All right. There's another clip where we look at designing a beam using SUMO FEA only. Now it doesn't yet make use of solids. That makes use of thickened or just plain shells. But we're definitely gearing up towards a space where we are going to delve more into the FEA space, and especially looking at design, and as well as comparing our code-based results with the results we get within SUMO. There's already some content on it, nothing specific revolving around using of solids, although the use of solids is part of our advanced analysis and SUMO intermediate training. So I hope that gives you some good information just to get started. And of course, you're welcome to mail me if you have any specific questions or scenarios you have in mind. So I hope that answers your question. And then, looking forward to chatting to you if you're interested. But all right, to the rest, hope that you have a fantastic week further. It's only Tuesday. We're going to get there, but I hope that you have a fantastic week and look forward to seeing you in future sessions.